Okay, good afternoon. We finished last week with the Kolbe-Schmidt reaction. And in the Kolbe-Schmidt reaction, a phenolate attacks carbon dioxide. And it does this by what looks like an aldol addition. It's topologically identical to give this carboxylate, which then, since it's the keto form of the phenol, undergoes tautomerization to the final product, which, since this is done with base, initially forms the carboxylate, and then on workup you can protonate it. And the reason, and the surprising thing about this reaction, called the Kolbe-Schmidt reaction, which gives rise to salicylic acid, or the 2-hydroxybenzene carboxylic acid, which is the precursor to aspirin, so it's a multi-ton process. The surprising thing is that the attack occurs selectively ortho. Okay? So I've written it and described it sort of like a pseudo-aldol type reaction, where this is, you can view this piece as the enolate, and this as the carbonyl component, and you get the addition, just like an aldol addition. You can also view it as an electrophilic aromatic substitution, where this carbon is the delta plus plus carbon activated by 2 oxygens, and it attacks a highly activated, unusually highly activated benzene ring, because it's not a phenol, it's a phenoxide. So it has as a substituent actually a negatively charged oxygen, which adds a whole negative charge into the pi system, which makes it super hot. And that will then attack, like in an electrophilic aromatic substitution, give you the corresponding intermediate, and then you deprotonate. The twist being that instead of the normal electrophilic aromatic substitution, where the electrophile is positively charged, like NO2 plus or Br plus or something like that, it's actually neutral, and it attacks a negatively charged benzene rather than a neutral benzene. And so after the attack has occurred, the resulting intermediate of the electrophilic aromatic substitution, instead of being positively charged, is actually neutral. Okay? So it's all just one charge shifted. Okay? Otherwise, the process is identical. And then the deprotonation occurs, and the reprotonation happens to be on the oxygen that is part of the substituent. So you can view this from both perspectives, and both of them are right. Okay? Both of these views of this reaction are complementary. And so the surprising thing was that it goes selectively ortho, and the reason for that was that we have a counterion sitting here, sodium or potassium, I think we wrote sodium, that is closely attached to, by Coulomb's law, to this oxygen, and because of its charge also attracts the lone pairs on the carbon dioxide oxygen, and basically pulls it in and directs it to go ortho. And there are many such cases where so-called directing groups control the site of electrophilic aromatic substitution. We haven't really gone much into that because this is sort of higher level chemistry. But this is definitely an example where you can perturb the normal para selection in an ortho-para situation that is typically enforced by sterics, such that you turn to advantage the fact that you can have stuff sitting around here, stuff other than solvent, that could direct the electrophile in this way. So one alternative to this is to actually incorporate an electrophile or an attacking species into an ether molecule derived from the phenol. And if you can get this guy to then attack the benzene ring, that would also only be possible at the ortho position. And this is the subject, the initial subject of today's lecture. And this reaction is called the Claisen rearrangement, named after this character here, Ludwig Claisen, who discovered this in 1912, or he published it in 1912, where he found that when you take this alloether, or allo-oxybenzene, I guess we would call it, or 2-propenyl-oxybenzene to be totally precise, when you heat it up, the product is this. It's an isomer. Okay? And you notice that what formerly has taken place is this allo group and the proton have traded places. The allo group now winds up here, and the proton winds up on the phenol oxygen. And it took a while to figure out what was going on here. This was, after all, in 1910, where chemistry was pretty young. And one of the things that people found out, including Claisen, found out by substitution, which I'm not showing you, I'm just labeling the carbons with color, is that this carbon, which is now labeled or not labeled, it's black, that's initially attached to this oxygen, is the carbon that actually winds up at the terminus. Okay? And the terminal carbon, which is green, winds up attached to the benzene. And you can do this easily with the substitution of salts, including deuterium labeling. So something very interesting was happening here, namely that this carbon at the end of this allo-oxy chain was attacking this carbon here, because in the end it winds up at this position. And after a long series of researches and advances in aromaticity, people realized that this is nothing else but a special case or another case of an electrocyclic reaction. So the next couple of slides really fit in perfectly an extension of chapter 14, where we discussed electrocyclic reactions. And the electrocyclic reaction that occurs here is a 6-electron transition state, aromatic, where you move, starting with a benzene ring arbitrarily, this electron pair out here to grab this carbon, that pushes this electron pair in here to make a double bond, and it breaks this CO double bond to make the carbonyl. Okay? Everything happens all at once. It's conserved. And the initial product is this species, which you now readily can recognize. It's just the keto form of the corresponding phenol. So in the subsequent step, just as we did here in the Kolbe-Schmidt reaction, the proton migrates over to the oxygen to regenerate the benzene aromaticity. And so this is named after the discoverer, Claisen. It's called the Claisen rearrangement, or more specifically the aromatic Claisen rearrangement, because it involves the double bond of a benzene ring, which is actually intrinsically energetically unfavorable or more costly than the alternative, which would be to get rid of the benzene ring and just look at the double bond itself, the isolated double bond. Nevertheless, it occurs, although one has to say this requires a fair temperature, 200 to 220 or so degrees. So if you have sensitive substituents, this is fraught with problems. Often you circumvent that by particularly if there are problems at higher temperatures of polymerization, that the two substrate molecules start bumping into each other with such velocity that other things start happening. With double bonds, there's always a chance of polymerization. You can do this in the gas phase, which basically consists of distilling or subliming your starting material under vacuum through a hot oven. Okay, so you have a starting flask here and a tube that runs through an oven. You heat up the oven, and on the other side you collect in a cool flask, you collect the product, and you warm up on the left, and it sublimes through the hot oven. And in the gas phase, particularly under vacuum, the chances of two molecules finding each other is greatly reduced. In fact, it's basically negligible under the conditions of most experiments, and so you avoid any polymerization. So tricks like that can be played to get around the relatively high temperature. But it does require reasonably high temperatures. But it is a very neat way to functionalize selectively a phenol at the alpha, at the true position, at the ortho position. If I were to ask you to make something like this or something derived from this, from phenol, you would, you'd have to think about it. Because typically a phenol would undergo electrophilic substitution here. So yeah, we've learned tricks to get around this in chapter 16. We can block para with sulfonic acid or with SO3 to make the sulfonic acid. And then you can do an electrophilic alylation or do a Friedrich-Crafts acylation and convert that eventually to this and the like. But this is a much quicker way of doing it because you can make the corresponding phenol ether by Williamson ether synthesis. Just take phenol, sodium carbonate or sodium hydroxide with the corresponding halide, propenyl halide, and you get this, and then you just heat it up and makes this. And the beauty is not only reads your selectivity, but the resulting product has a double bond in it, which you can go to town with in terms of further elaborations. Okay, all kinds of addition chemistry. You can functionalize this molecule quite readily. So that's a useful transformation. That occurs also with substituents. So you can put substituents, methyl group at the CH2, or methyl group at this CH2, or methyl group here, or methyl group here. It all works. Okay, so this is the so-called aromatic Claisen rearrangement, and this is to be contrasted with the aliphatic. But before we do that, let's back off and remind ourselves what we discussed in Chapter 14 and how the Claisen rearrangement is related to Chapter 14. In Chapter 14, we did electrocyclic rearrangements. The closest one would be hexatrine. Okay, where we have 3 double bonds. They whiz around in the transition state, and we get the thermal ring closure. Remember, this went to this rotatory in this 6-electron case to make cyclohexadiene. Okay, and in the Claisen rearrangement, we also have a cyclic array of 6 electrons, and there is a weird oxygen in there. But in fact, it didn't take people long after the Claisen rearrangement was discovered. In fact, it was this guy who thought about this, Arthur Cope at MIT, a couple of decades later or so, that one could, in principle, do a similar rearrangement with an all-carbon case, okay? Namely 1,5-hexadiene. So in the Claisen rearrangement, we had one of the double bonds was a benzene ring, and then there was an oxygen. He said, why not just take a double bond and no oxygen, just 1,5-hexadiene? It's the same movement. In fact, now recognizing this, and this happened today, this morning in class, after class, people came up and said, could you do this one? Could you do that? Indeed, you could. Any arrangement like this, you can substitute any of these carbons with some other heteroatom or substituents and the like. And in principle, that rearrangement should occur. So in the all-carbon case, this is called the Cope rearrangement, named after the discoverer. And without substituents, you can readily see, if you remove the benzene ring, the Cope rearrangement is actually degenerate. In other words, the product is the same as the starting material. The connectivities have changed, but if you don't label, you don't know that actually something has happened. So in order to show that something's happened, you put substituents on. So for example, with phenyl here, you heat this up, and it goes to this side. This is initially an equilibrium, of course, but the equilibrium lies on the right side because the benzene ring in the product is in conjugation with the double bond, and that's more stable by 3.5 or so kilocalories per mole. Okay, 3.5 kilocalories per mole doesn't sound like much, but in an equilibrium situation, it is a huge equilibrium constant because remember, 1.36 kilocalories per mole equates an equilibrium constant of 10, and if you double the 1.3 to 2.6, that's 100. Okay? So 3 to 4 is 1,000, the equilibrium constant of 1,000 to the right. So this is also a very useful transformation that allows you to transpose substituents quite readily. And you notice that the similarity of the Cope rearrangement to the one that we discussed in Chapter 14, the hexatrine ring closure, is profound. It's simply, here we're moving a pi bond. What we're doing in the Cope rearrangement is we're moving a single bond. Okay? So consequently, this is a slightly stronger bond. Sigma electrons are more tightly held than pi electrons, so you need slightly higher temperatures, or noticeably higher temperatures. This one here you can do at 80, 90 degrees. This one you need 180 degrees. But the principle is the same. It goes exactly the same way. So dwelling further on the Cope rearrangement, on the actual parent, the way you can show that this degenerate Cope rearrangement occurs is by putting deuterium label on it. That's the minimal perturbation of the carbon framework. Basically, deuterium is the same as hydrogen. It's just twice as heavy, and there's some in terms of vibrational energies, because it's heavier, it has different vibrational energy of the CD bond, but this is a minuscule perturbation. And so, but you can follow this very nicely by NMR. Okay? So if you look at this as a starting material, it has no signals for the saturated carbons because they're all deuterated, and it's got only signals for the vinyls. Now heat it up, it sets up an equilibrium that will be 50-50, okay? Because there's no driving force. The deuterium doesn't add in any position any noticeable stability. But now in the product, you can see now they're saturated hydrogens that will show up in the NMR spectrum. And so the peaks that are missing as you do this reaction will start growing in. You get signals for this. And the signals for the terminal CH2 groups will diminish because 50% of this position will now be deuterated in the equilibrated compound. If you can't follow this, it doesn't matter. The point is you can show this very nicely by NMR. And one can also show this very nicely in a movie made by my colleague Stefan Immel from Darmstadt, who based these movies on high-level quantum mechanical calculations, so you get a pretty nice picture of a pretty accurate picture of including bond length changes of what's going on here. And so he's going back and forth in this rearrangement. So this is the degenerate 1,5-hexadiene rearrangement. 2 double bonds start at the end, then you form a bond here, and now they're at the other end. Okay, and it just goes back and forth like this. And if you stare at this a little bit and watch it in the middle, halfway through, you realize it's basically 2 allyl radicals in a way that are interacting across the 2 termini. That sort of windshield wipe back and forth. Okay, weep back and forth. So it's a very smooth movement. Okay, so without substituents, it's degenerate, so you need to put substituents to show that it's happening. And one of the things that one can frequently predict based on basic knowledge that you have, like conjugation or more substituted double bonds and the like, you can predict where these rearrangements lie. Here's an example where you can clearly predict where the equilibrium should lie. This is the quite famous dithionyl-cyclopropane rearrangement, which occurs relatively readily because now this CC single bond is actually quite a strained bond. So this occurs at lower temperature, and if you move the 6 electrons around in the usual 6-electron transition state, you get this. You make a carbon-carbon bond across here, and you break this bond here. And that gives you the 1,4-cycloheptadiene. And this is clearly completely lying to the right because you've released the 28 kcals or so of ring strain that are embedded in the cyclopropane. So back to the original Claisen rearrangement, you can now see how this works. This is just a modified Cope rearrangement, if you wish. So the names are all meaningless. It's really electrocyclic closure, and in this case, making closure and ring opening, making one single bond and breaking another single bond. And it just so happens that the molecule in which this was discovered by Claisen has one of the double bonds being part of a benzene ring, and one of the Cope carbons is actually an oxygen. And so this shows utility in substituted phenol transformation. It didn't take Claisen very long to at least recognize, he thought that oxygen was necessary, but at least to recognize that you didn't need the benzene ring. So he did try in the same paper, in fact, it's a minor portion of this initial paper reporting this thing, that one could also do this on the non-benzenoid system, where, which was called the aliphatic Claisen rearrangement, meaning it's non-aromatic, where the double bond that is in the original Claisen rearrangement part of the benzene ring now is just a normal double bond, and it occurs the same way. Okay? You need fairly high temperatures, but you do the electrocyclic whipping around, and here is your oxoalkene, or your aldehyde in this case, where you're generating this carbon-oxygen double bond, just like you generate the carbon-oxygen double bond here. Now the difference is here, this guy is unstable to keto-enol tautomerization. In the aliphatic Claisen rearrangement, it just sits there. It doesn't transform any further. So this is a very neat way of making an aldehyde, starting with the corresponding ether. And this is clearly lies also to the right because the carbon-oxygen double bond is such a strong bond. It's stronger than the carbon-carbon double bond. And so we can look at that also in a Immel movie, and you'll see that it's almost identical to the previous movie, except that now one of the carbons is an oxygen. And it's labeled red, so you can clearly see it. So you start with this compound here. Okay, there's the ether linkage, and it breaks, and you make a carbon-carbon bond at the other end, and now you get a CO double bond over on the right. Okay, so keep that in mind. It's actually quite easy to memorize or to keep the picture in mind. It's basically 2 3-carbon or 3-atom species that are like allylic radicals that keep linking at the 2 termini reversibly. And you, if you want to predict where the equilibrium lies, whether the reaction is exothermic or endothermic, you look at the 2 products and make a decision. And so in this case, it's clearly the CO double bond that drives this quite selectively. Okay, so after that little interlude, back to chapter 14 in electrocyclic ring closures, let's finish up what we can do in our discussion of what a benzene ring does to substituents. And most of our discussion really in the last lecture was concerned with phenols. What does the benzene ring do to the hydroxy function? We briefly touched upon amines, because we can make amines using palladium chemistry from the corresponding haloarenes. And so now let's look briefly at what the benzene ring does on the reactivity, for the reactivity of the amine function. First of all, I should say that these guys can be acidic, basic, they behave like normal amines. Okay? So it's a perturbation that you have a benzene ring here. And one of the things that it perturbs is the availability of this electron pair. Okay? And we've actually already talked about this briefly in the amine chapter. This electron pair is tied up with resonance into the benzene ring, as you can indicate by writing resonance forms. So this electron pair kicks in and writes a dipolar structure with a plus charge of nitrogen and a delocalized negative charge on the benzene ring. And this means that protonation is not as easy, as readily done as a normal amine, an alkane amine. Okay? And that means that the corresponding ammonium salt is quite acidic, much more acidic than a normal ammonium salt. Normally, it's around 10, 11. This guy, benzene ammonium, is 4.63, so it's 5 pK units, 100,000 times more acidic, because the corresponding base is actually more stabilized. This lone pair is delocalized into the benzene ring. The nitrogen can be acylated. You can make amides. It can be alkylated. You can make alkylamines. You can do reductive aminations using this as a substrate in the presence of aldehydes and ketones. It makes imines and so on. So otherwise, it does everything that normal amines do, a little less ready so, because the alone pair is slightly less available. But otherwise, so this is a quantitative aspect that we won't go into. You can make it do everything that a normal amine does. But one thing that's unique about this is the conversion of the amine into a diazonium species. And remember, this is done by taking sodium nitrite and acid, which makes nitrous acid, HNO2. Under acidic conditions, it forms NO+, and the NO+ attacks to give the N-nitroso compound, and then we rearrange the protons by tautomerism. We did the mechanism, although I won't test for that. But the net result is that we can make diazonium salts. And remember, you may remember that when the substituent to the amine, and therefore the diazonium cation, is alkyl, these guys spontaneously decompose. If it's concentrated, they explode, because the nitrogen just takes off regardless of what it's leaving behind, any carbocation. Okay? And so they were useless because of that. But in the case of benzene diazonium, these guys are actually sufficiently stable. They're still hot species, I should say. And so they're typically not isolated, because if they're isolated and dried, especially,